We're going to talk about some bugs based on unwanted side effects. In front of you, you see a picture of the world's first captured computer bug, 1947, Harvard University, and you can read that later, but it gave them wrong answers to something they're working on. So we're going to look at hidden adverse side effects. Here's a positive side effect. If you read it correctly, it says z equals 2 times 4 is 8. Z equals 8 is the side effect, and it's positive. I want that side effect. So I'm going to show you a piece of code. Take a look at it and tell me what you expect, or think to yourself, what would you expect the output to be? There's nothing tricky here. It's straightforward. It's just your expectation. Turns out when this code runs, it doesn't give us what's expected. I would expect to see hello John and 2 times 6 equals 12, and I see that, but at the end it says by Spider-Man. All right. That was completely unexpected looking at that fragment of code. There's nothing in this fragment of code that says that. So notice I did say this was a fragment of code. It means it's a part of something much larger that we can't necessarily see all at once, that things are happening in our code. So how could it have happened? Well, looking up somewhere above our function or fragment, we'll find there's might have been a global variable user, and somehow inside the ×2 function was the adverse side effect. User was equal to Spider-Man. How could that happen? Maybe a programmer was debugging the code and slipped this line in there for diagnostics purposes, and then it was released later on, and we found it. So our lessons are: avoid global variables in functions. Global variables can be dangerous, and a function's name should do exactly what it says, nothing else. So here's a nicer rewrite of that function. ×2, pass it an integer, we'll call the integer x, 2 times x, and we return the value. Nicely encased. So now when we run our code, it runs exactly as expected. There are no tricks. Another illustration. This just highlights that in general you might say, well, global variables, how bad could they be? Avoid things like that. Well, they can become demanding. So here I have a function called molt, and it relies on 2 global variables, a and b. Right. You would say z is encapsulated. No one sees z. That is, the caller cannot see z. And a and b are global. And we're going to use the molt function. You see some ellipses there, ... It's basically saying somewhere in my code, and I might be using this time and time again. I set a equal to 7, b equal to 2, and I say molt. All right, but what am I really doing here? I really have to, as a programmer, keep track of this a and b are no ordinary a and b. They're global a and b that are used by molt. And I don't know how it's used. That's why I blotted this out here. I don't know what's going on in there. But I do know that somehow it will use a and b. And I have to remember this. Programs can become quite large. This is a much better design. Everything is encapsulated in this function called molt. You give it some integer, give it another integer, it multiplies them somehow, and returns the answer. So there are 2 things going in. one thing coming out. This is a way to look at it. In fact, we have no idea what's inside that mult function. We just know it magically works. I doubt there are Lego pieces in there though. And here's how we use it. Notice I don't have to keep track of an A and a B. Any place I want to multiply two numbers, I just say mult. So what do we know? We want to encapsulate, 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 as the Darlax might say. Yes, another illustration. This one is a function f. I'm going to pass it to number 4, and I'm going to do it again. There are no global variables, and I have not encapsulated it. I mean, everything is encapsulated. All right, so no global variables, everything's been encapsulated. When I run this piece of code without global variables, I get different outputs. It's encapsulated. Yeah, when I run it, I get different outputs. How could that be? There's a word called static. And if you create a static variable, the variable lasts for the lifetime of the program. So here you'll see I have a static. I call the variable hidden. Why? Because I could have called it z, but I decided to call it hidden. And I set it equal to 0, and I tell the compiler, once you see this variable and it's created, keep it for the rest of the program. So unlike a normal variable declared in a function, a static one stays around. That is, normally variables are destroyed when the function returns. Yet this one is not. So we can add this other concept. We have the idea of no hidden inputs, that is, no global variables. There are no adverse side effects that are hidden. Everything is obvious. And a third bullet is added there. Given an input, the function will always yield the same output. This is for functional programming, which is beyond our scope here. But here's a pure function. No matter what you do, it always gives you the same answer. It's completely encapsulated. There are no global variables there. Here you'll see there are no global variables, no hidden adverse side effects, and when you doesn't retain history in any adverse way. Give it an A and a B, you always get the same answer. So maybe after all this is done, maybe our lesson is, all right, no matter what you do, there's going to be some sort of bug in any large program somewhere. That's why there are updates. I hope this is useful. Have a good day.